welcome. Today we're going to be talking about independence of path. And so this is about line integration. Okay, so line integrals, the type we're talking about is in force fields. Okay, so what we're talking about again is doing a work, computing the work over some path, which we'll call C, of the vector field F dot dr. All right, so again, we have some vector field, which is, we'll put it in the plane for now. And in the vector field, there's every point in the xy space. There are vectors, like so. So the question then is, and we have some path going through it, like there, from, we start at t equals a, and we go to t equals b, and the path we take is going to be determined by this vector function r of t, x of t, y of t, like that. Okay, and so one way to write this is you go dr dt is equal to x prime y prime, which allows you to write dr as x prime y prime dt. So we can rewrite this as, so here again there's the path C. We can write it as from A to B, f evaluated at x and y of t, dotted with the vector r prime dt. So that makes it a concrete integral that we can compute constructively. So we learned last time, recall, if our vector field is what we call a gradient field, that is, we can write f as the gradient of some scalar function. We call it a potential function. Then we learned something very important, which is the fundamental theorem of line integrals, which is the integral C over the vector field dotted with our path. The work completed is independent of path, or rather, all it depends on is the endpoints of the thing. So all it depends on is, we can rewrite this as our gradient field, and it's equal to f evaluated at the point r at time b minus f evaluated at the point in the plane at time a. All right, so and we learned that it really doesn't depend on the path at all. So you can take from this point here, going like that all the way over there. We could also take another path to get to the same location. So we can go this way to get there, or that way, provided the gradient field, providing that our vector field is a gradient field, it doesn't matter which way. All it depends on is the endpoints. And this is an analog of the fundamental theorem of calculus. So one wonders then, if we have two paths, we'll call this path C1, and we'll call this path C2, and they both share the same starting and endpoints. And let's say we call negative C2 be the reverse path. So the reverse path, what we need to do is run time in reverse. So time has to go from B to t equals a. And that means that our delta time intervals will go to a negative interval because we're going backwards. And then if we're on a path like this, and our velocity, r prime, is pointing this way, because we're going the opposite direction rather than going forward over this way, we're going to go backwards. So we need to have a negative r prime going the other way, because now we're going to head this way, back. And so the integral over this reverse path can be written in the following way. So that becomes integral from, we're starting at B and going to A. And our vector field's always the same. But then we're going to dot it with a negative r prime. And then we're going to take time in reverse. So we're going to move that over. So these two negative signs cancel. But we see we can also switch A and B in the integral. So we can go take a negative, starting from A and going to B, of f dot r prime dt. And that we can write as negative c, or the negative integral c2 f dot dr. So if I want to go backwards through our path, it's the same thing as going forwards through our path to compute the work, and just appending it with a negative sign. So that's a nice result. We should be able to do that. So now if I have a closed path, so with these two paths, so if I take C1 and I union it with, I take that to be big C, I'll call it capital C here, and I union it with the negative C2, I should get a closed path. Closed path, or what we call a loop. All right, and of course you can easily see that because these two integrals are the same, because they're both independent of path, we can write C, this capital C, of f dr is going to be 0. The work done computed to go here will be simply the difference between the endpoints evaluated by the potential function. But to go back, we have to, of course, take the difference of the endpoints of the start and end. But those will, of course, be a negative of the original result. And so the net will be 0, because this literally is C1 f dr minus C2 f dot dr. Right? And we know that these are both equivalent and they're subtracted together, so it has to equal 0. So closed loop paths, as long as our function, so this works, of course, only for gradient fields, where we have this result here. Okay. So the question is, and today we're going to explore this idea a little further, of what it means to be, what qualifies a vector field to be independent of path, and how do we find f, the potential function, little f, and how do we determine things, the nature of these gradient fields and things like that. So now that we have the idea of a closed loop, we can use this to write down a few results. So the first theorem, we'll write down a theorem here. So the theorem is pretty straightforward. If the vector field f is independent of path, I'm going to call that IOP from now on. And we're going to say in the domain D for the function, so this is our domain. Okay, if and only if the work computed for any closed path is equal to 0 for every closed path. And what we mean by closed path, we mean some sort of loop, okay, in D. All right, so let's say we have some D, and it's some sort of set where our function is defined, and there's vector, it's a vector field of some type. So if I pick a path in there and it goes around in a circle and I come back to the same spot, if the work that's computed over that force field is always 0, and that's for every path I can pick, any path I can think of. If they're all 0, if this is true, then just as we've written, f is independent of path. Okay, and that means, and that's the definition then. If you want to call that a theorem, or you might want to call that a definition. Okay, so that's a nice result. So let's go a little further and try to figure out, and I'm going to do one more thing here first. Sometimes we also see this integral, they'll put a little circle around that, and that means that it's a closed path integral. All right, so closed path integrals, sometimes you'll see this notation. So it's just a notational thing, and I'll use that a little bit. So this is nice, but not useful. If it's not useful to determine if f is independent of path, or otherwise what we call conservative. Okay, otherwise what we call that there exists a function f such that the gradient is equal to f. All right, so how do we fix this issue? So why is this not very useful? Well, it's not very useful because there's no real constructive way to check every closed path in our domain. There's infinitely many. We can keep trying examples, but we'll never be able to check every single one because there's infinitely many. And because of that, this is a nice definition. It's certainly a good way if we can find one closed path where it doesn't equal 0, that certainly helps us determine that yes, our function is not conservative. Our vector field is not independent of path. But in general, it'd be hard to actually state that our vector function is conservative or independent of path with this definition. All right, so what do we need to do? So the question then again is how to determine if f is independent of path. Okay, that's the question. So let's go dig into what f is a little bit more. And we're going to just do this for the plane, but a lot of what we can do could also be translated to 3 dimensions as well. So this is f, and it's a function of x and y. And we can write it as a vector, p x comma y, and q x comma y, right? So those are the 2 functions, the 2 components that represent the x and y components of our vector field. And they're defined for every point x, y in the plane or in the domain of interest that we're thinking about. So one thing we can do is we can actually check this by, so if there's a function such that this is true, well, one thing we could do for sure is to anti-differentiate. It must be then that partial of f dx is equal to p. It would imply this, and that the partial of f with respect to y is equal to q. All right, so we could easily enough anti-differentiate. And see if we get, we'd want to check if this leads to f. And we want to check for both p and q that this was true. So again, we don't know if this is true, this equal sign here, but we want to check it. So we write it down like that. Oops, sorry. So we'd anti-differentiate q with respect to y and anti-differentiate p with respect to x and see if they're equal. We want to check to see if those two are equal. Now the problem, of course, with this is we always have to add that plus c, this constant. In this case, it's a constant, an integrating constant in terms of x. And here, there's always an integrating constant. Actually, I'll call that k of x. And here, there's always going to be an integrating constant we'll call that k1, and this k2 of y. And so when we take that derivative, x, any function that's only of y will just disappear completely from our problem. So we have this problem where anti-differentiation doesn't really help us. But what about the other route? What if I know that f, some function with respect to x, whose derivative with respect to x equals p, and some function whose derivative with respect to y is equal to q. If this is true, it must be then that if I take the derivative of y of our function p, and again I want to check this, is the same thing as the derivative of f with respect to xy. We want to see then again that these two are equal. All right, and so that has the problem of not having to deal with these constants. Right, so that's one thing. So of course, if this is true, then and we see here that we have the order of the partials are different here, but we know that as long as f is continuous and it's differentiable, that switching the order of differentiation is no problem. So the question then reduces to, is this true? So if this is true, if the p and q that we're given for our vector field, if we take p, the partial with respect to y, and q, the partial with respect to x, and they happen to be equal, then that certainly is one way we could possibly determine if f is conservative. There is a little hitch here, and this is a very difficult theorem to prove, but we'll state this theorem now, which is it'll be a very difficult theorem. It's a difficult one to prove, but we'll state what it is. So, and we have to be very careful when we write it down. So we have this issue. So we're going to write this down as a theorem. If our f vector field is equal to p comma q, and we have the following statements are true, we'll call this A, that p with respect to y, the derivative with respect to y, is equal to, and if the following statement is true, and q with respect to x, if these two are equal, and, this is another key point, this is true, f and a are defined and a is true on a set D that is what we call simply connected, then the final result, f, is conservative. And that's the same thing as independent of path, which is the same thing as there exists. We'll use our there exists symbol, or backwards e, in f, such that the gradient of f is equal to capital F, the vector field. Okay, so what do we mean by simply connected? That is something we haven't yet defined, so I'll define it here. D is simply connected if the set is connected, and that means that all paths are all points can be connected by paths C in D. Okay, that's a parenthetical, and there are no holes. What do we mean by holes? And again, we're thinking about a set like this. So D here is simply connected, and that if I have a point here and here, any 2 points, I can always draw a path between the 2 points, and the path itself is also inside of D. All right, so here's a not simply connected. It'd be something like this, where there's again some sort of hole inside of the set, right? So this is like some sort of donut. In this case, the path, 2 points that are inside the set, you can still connect them by a path, but there's this problem here where there's a hole inside the set. Something about the vector field that we've defined, there's some area inside of D, a hole if you will, where f isn't defined or the derivatives aren't defined. Okay, so and then the other example of being not connected would be if you actually had, if D actually had 2 pieces, right? And so in this case you have 2 points, but there's no way to connect them by a path that's all in D because there's some gap between. But the real interesting one is this idea of a hole. So this turns out to be very important, and it's sort of the gateway to a lot of modern mathematics, this idea, but it has some very important consequences for things that are very relevant for science and physics and engineering. The idea that sometimes the sets that we're interested in, the domains by which our functions are defined on, have holes. And those holes then are the real blocker that will not allow f to be conservative or independent of path, or we cannot find a potential function. So let's do some examples of determining what f is. So I'll pull up another sheet. Okay, so we're going to do 3 examples. Of f, and we want, again, the goal here is f independent of path. Okay, so we're going to talk about a really simple one first, example 1, and that is the example of what if f is a constant? When I mean a constant, I mean it's a vector constant, so it's just going to be, so we'll talk about an example of the vector field 1, 2, right? So in this case, p of x comma y is equal to 1, and q x comma y is equal to 2. All right, so what does that look like in the plane? It seems as though then at every point in the plane, the vector field is the same vector, right? So go forward. So at the origin it's that way, and every other point, the vectors always point in the same direction. They have the same magnitude, and we can tile out the entire plane with the same vector, like that. All right, we want to know is this vector a conservative? Is this vector field conservative? So let's try. So again, our theorem was, is the following true? Well, certainly. So what is p? So the partial with respect to 1 of y is of course 0, and the partial with respect to q is also 0 because they're both constants and the derivative of the constants are 0. So that's good. The next test, so that's part A, and the part B is the domain, is D simply connected? And the answer is yes. Are there any holes? This thing is defined for the entire plane. D is entire plane. Okay, so that the entire plane, of course, every point on the plane can be connected by a path. And yeah, there are no holes. Okay, so no holes. So both are true, and therefore we can define. So we know that f is independent of path. So we can do a little quick calculation here. So first of all, what is little f, right? What is the potential function? So now we can go through and actually figure this one out. So so we might not be able to find a unique one, like you said, but we can certainly find a potential function that would be true. So let's talk about how to figure this out. So we know that p is equal to 1, and if I take the antiderivative with and that's equal to partial of f with respect to x, and therefore if I integrate that, if I anti-differentiate it, we should get x is equal to f, but we have to add a plus, again, that k1 of y, which is some undetermined constant that is a function of y. Likewise, we do the same thing for the q. So again, q was 2, so that's 2 is equal to partial of f with respect to y. And we anti-differentiate that with respect to y. And we get 2y plus what we'll call k2 of x, any function of x that's only a function of x. When we take its partial with respect to y, it goes away. So again, there's these mysteries. So of course we have, and that is also f of x comma y. So now we have to equate them. So k1 y plus x is equal to 2y plus k2 x. So we can easily see that k2 can be considered x, and that k1 can be considered can be equal to 2y. The only thing is we still have a non-uniqueness problem. So what we can write down then is f of x is equal to x plus 2y plus still we have an undetermined constant. I'll just call that constant c, and so that is just a number. So again, anytime we take a partial derivative to get our vector field, any just constant is going to disappear from our problem entirely. So there we go. There is our potential function. So clearly, if you write gradient of f, we get back out 1, 2, just like desired. Okay, so there's one example, and that's a very simple example of a conservative vector field. We could also go further, and let's just verify independence of path. What if I take a path? So let's take r is equal to the circle around the origin. Of course, then r prime is equal to negative sine t cosine t. Oops. Running out of room. All right, and that means that I'm going to take, so I'll take my work then will be the integral over our path, which is just going to be a circle, over our vector function f dr, which is going to become, and we're going to roll this from 0 all the way to 2 pi to go around in a circle. I'll go from 0 to 2 pi. It'll be our function f. F is a vector field 1, 2, dotted with r prime, negative sine t cosine t dt. All right, And so we can write this like this: 0 to 2 pi negative sine t plus 2 cosine t dt. And we know that sine and cosine are periodic functions. Over the interval 0 to 2 pi, half the time they're above 0, and for the other half the time they're below 0, and they have equal area under both above and below. So we know this integral has to be 0. So that, of course, that just verifies, at least for one path, that we do have closed paths integrate. The work computed over that path will always be 0. So that's just a nice little check that these sort of things work. And the idea is pretty straightforward here. If I have some path, and I'm going around like this, and again, I'm thinking about this as a force field, and if we think of this, we like to think of this as maybe the direction that the wind is heading, maybe, or something. So half the time we're going downwind, right? The wind is blowing kind of at our back, and then here we appear to be going right across the wind, so there's no forcing on our path that way. It's all cross. But then all of a sudden we're working against the wind here, and we have to actually put some work into it. But then we get no wind as we go through here, and then the wind's at our back, so we're pushing. So for all of the pushing we do going this way, we also get another half of the circle. The wind is pushing us back, so we're doing negative work. And so the idea here is on the balance, the net work that we do is 0. So that's again another example of independence of path. So now let's talk about a more complicated example. So this will be our example 2. And it's going to be the vector field 2xy comma x squared minus y squared. All right, so so what we do always, okay, so that's our p and our q. So what we'll do is we'll do our test. So we want to test p and q. So p, we take the partial with respect to y. We do that, we'll get 2x. And then here we'll take the partial with respect to q of x, and we get 2x right here. We take the derivative with respect to x. So obviously those two are equal. So that part of the theorem checks out. The next part is the region D. What is D exactly? Well, f is defined. It's continuous, it's smooth on entire plane. Okay, so there are no holes, and it's connected. So the theorem should say then f is independent of path. That's what we deduced from the theorem, and also there exists some potential function such that the gradient of it is equal to capital F. So let's try finding that real quick. It's pretty straightforward to do. Again, we have to anti-differentiate. So again, we have P, and now I want to anti-differentiate with respect to x, and that's going to be equal to our f, and that's going to be x squared times y plus, and again I have to put that k1 of y there. We always lose constants in the other that are functions, or I should say functions of the other variable. They're constants with respect to x changing. Okay, so there's that. So that's one half, that's one piece of our, so then we have to do q, and we anti-differentiate with respect to y to get our f, and that is also going to be, we can see there, so we have to anti-differentiate with respect to y, so that's going to be x squared times y minus y cubed over 3. All right, and then we again have to add k2 of x sitting there. So of course we equate them together, and we can see that k1 of y has to equal negative y third over 3, and k2 of x is a mystery, We don't know what it is, but it could be some other. It could just be just a constant. So in fact, it is just a constant. It's just it could be some constant value, and that's the non-unique. So put a little that there. So f then, x comma y, our potential function, is going to be x squared times y minus y cubed over 3 plus some undetermined constant that will go away when we are when we compute the gradient field. Okay, so that's nice. So there's our potential function. All right, so now we're going to go to a final example, and I know you're probably getting tired, but this is really, I truly believe it's worth it. So this example is one that's really going to show something that's very important in physics and something that is very interesting, as we'll see later on as we go further in the course. So let's try this one. Actually, hold on. I'm going to define this in polar coordinates first, and we'll switch to rectangular in a second. This will be 1 over r cubed times the vector negative sine theta cosine theta. All right. So how do we write this in polar coordinates? Well, one way we do is I can multiply this by r. I can sorry. Apologies there. We're going to back up a second. That's not a 3. That's just the first power. Okay, so we'll do that. But now what I'll do is we'll still make it 1 over r squared now, but we'll multiply an r on the top and the bottom. We'll get sine theta cosine theta times r there. All right, so that of course is y, that of course is x, and that we can write as 1 over x squared plus y squared times the vector negative y comma x. All right, so what does this vector look like in the plane? It's at the point here, it's going to be pointing up, and the point over there, it's going to be pointing to the left. Likewise, we'll do this. So it has a sort of vortex-like swirl, right? So as we get further out, as we go further away from the origin, of course, the vectors still are sort of in a circular orientation like this, but the magnitudes get smaller and smaller. And as you get closer and closer to the origin, of course, the magnitudes of these vectors get very large because 1 over r is going to start to, it's going to get bigger and bigger and bigger, right? So we have a problem right at the origin where r isn't really defined. So our vector field isn't defined at the origin. Of course, that's going to play an important role because that's our hole. Okay? At the origin, we have a point where our vector field is not defined. It's discontinuous. And so that will play a huge role in the consequence of this vector field. All right, so let's so this is of course then our p in this case is going to be negative y over x squared plus y squared, and q in this case is going to be x over x squared plus y squared. All right, so as always, our first check, our part A of our theorem, again, we want to find out, is this vector field conservative? And so we take the derivative with respect to y, and we get negative 1 times x squared plus y squared minus a minus, so we get a plus y. We take the derivative with respect to y, so we get a 2y, and all over the bottom squared. That is the quotient rule. All right? And that becomes y squared minus x squared over x squared plus y squared, quantity squared. All right. And also the partial with respect to x of q will be x squared plus y squared minus x times 2x over x squared plus y squared, quantity squared. And we get the same result here. It's y squared minus x squared over x squared plus y squared, quantity squared. Oh, so clearly these two are equal. Okay, so they're equal, so our theorem looks so good so far. But remember, f, or I should say, D has a hole at origin. Okay, so these derivatives, the derivatives here won't be defined on that hole. The function itself isn't defined at the origin, so there is a hole. So our D, if you will, if you want to write it, will be the entire plane. But we're going to have to excise the origin. We'll have to put we'll have to cut it out, so to speak. Okay, so that's nice. But that means that well, the consequence we have here is something very interesting. We'll get to it in a second. If I have a path integral that goes around that hole, like that, and it's a closed loop, of course I can move this path integral a little bit. I can make it bigger. I can even make it really oblong like this. But there's no way to continuously deform it and actually get it off that circle. In a sense, it's sort of hitched to that hole. We can't drag it through. The minute we cross the origin there, if our path integral crosses the origin, we have a point where there's a division by 0, and our work integral can't be defined. So there's no way we can untie or unhitch any path that goes around that circle. There's no way we can continuously do that, untie our path integral from that hole. And so that hole sort of anchors all paths around origin. Okay, and we'll see that has a really important effect. So actually, let's verify. Let's compute a path integral. So we'll say C is going to be our circle again. So R is going to be cosine of t, sine of t. And in order to compute the path integral, we always take R prime. And that's going to be negative sine t, cosine t. All right, so now let's do our path integral. So let's go back up to the polar form. So along this unit circle of unit path length, f of t then is going to be equal to, well, the radius is 1, so r is equal to 1, and the theta we can think of as being t, so our vector field over that point is going to be negative sine t cosine t. All right, so the path integral, so the work around this path, we always do our paths counterclockwise. That's one important feature. We always want to do that, and we'll see why later. That'll just be a convention. It has to do with something we call the right-hand rule, but we'll get to that in a bit. So our circular path integral over our circle is going to be negative sine cosine dotted with r prime, which is going to be negative sine cosine dt. And so that's going to, sorry, this isn't a path. We should put this from 0 to 2 pi like that. And of course, sine and sine makes a sine squared plus cosine squared. That's what this dot product computes, dt. Of course, that is 1, and we're going from 0 to 2 pi. So the result is 2 pi. And that is clearly not 0. All right, so we see here that a circular path, a closed loop that encloses this circle, it has a problem. We can't seem to get around it. At any rate, the point here is that this hole really did create a problem. A path in our plane, when we computed the path integral on a closed loop, was not 0, even though it appeared from our basic result, from our P and our Q, that it seemed like maybe we could find a conservative vector field that would produce a conservative vector, or a potential function. So there, and we're going to use this more and more, this idea of a hole, because a lot of times we have force fields that have a 1 over r or a 1 over r squared type dependency, and these of course all have divisions by 0. So these holes become very important in how we compute our path integrals in space. Okay, so thank you very much.